Okay, then let's move to the next question. So let's check the answer. One second, guys. Yeah, so we are having the water table. So I'll use my mouse. Meanwhile, so for calculation of the effective stress, okay, I'll use this thing, pen. Yeah. So your sigma dash effective stress is given by tan into gamma bulk minus tan into 10 into gamma into 10 into 9.81. Let me check why it's not okay. Yeah, so you are having sigma dash. So you are having the effective stress. Come on. Yeah, now I can work on this. So your sigma dash is given by gamma into H minus your gamma water into H, right? Assuming that your gamma water as 10, so your sigma dash is given by 80 kPa. Then you have to calculate gamma 10 minus 10 into 10. Yeah, So your gamma value will be 180 by 10, which is your 10. Yeah, sorry for that. So your gamma value is 10 kPa, sorry, 10 kilonewton per meter cube. Then you have been asked if the water table is lowered by 3 meter. So initially your water table was available here. Now let's say now it is lowered by 3 meter. So whatever your H is available, so how much is the reduction? Okay, so since the water table is lowered by 3 meter, so again there will be rise in the density of the soil. So at what factor your effective stress will get increased? So that will again your by gamma water into delta H. Okay, so this is the preliminary way I want to show you. So let's say by 10, if we are assuming the unit weight of water and your delta H as shown is 3 meter, so we can expect a rise of 30 kPa. Okay, so initially it was given at the below the ground surface was 80 kilometer per meter square. As soon as your water table is getting lower, so there will be rise in the effective stress, and how much will be that rise in the effective stress? That will be by factor of gamma water into delta H. So your change in water table is the 3 meter and your gamma water as we have assumed is 10 meter. So we can expect that there will be increase in effective stress, and that too by 30 kPa. So your gamma is 10 kilonewton per meter. This is the first method. Then the second method, like you can go with the conventional manner again. So then you need to solve the simultaneous linear simultaneous equation. Then in that case, uh, your sigma dash, so 10 meter below the ground surface. Yeah. So now your sigma dash will be gamma into H again. So how much is your gamma? That is 10 into 10, and then you are basically saying okay, so it's not 10 into 10, so that will be your 10 into 3, because there is no water table. Then you'll be your, I'm so sorry for that. Okay, so you are having this thing, then this is your 3 meter. Okay, this is 18, my bad. Yeah, so your sigma dash will be 18 into 10. Okay, and then how much is this decrement? So initially your water table was here 10 meter, so your effective stress here was initially was 80 kPa, and with the help of that we have calculated 18 kilo. Now it has been lowered by 3. Yeah, so now you are having the 7 meter available here. So 18 into 10 minus 7 into, again unit weight of water is 10, so 180 minus 70, that will basically give you the 110 kPa. So yeah, so the correct answer is your water table is being increased approximately up to the 110 kPa. Yeah, so that's how you can approach in two manner this particular question. So if you know the definition of the effective state, so then you can deal with this one. Any doubt in this, guys? If so, please let me know. This is not that difficult question, but yeah, due to that particular calculation, it become cumbersome. But yeah, now it's fine. So if you are having any query, please let me know. So this type of questions you can expect a lot in your gate exam, and if you guys are appearing for the gate again, so you can expect such type of questions. If you are having any query, please feel free to ask. If not so, then let's move to our next fundamental question. Yeah, here you need to give the definition of the quicksand. Please give your answer in chat box if you know any. Yeah, so let's look upon the answers. We do have answers from some of our learners, so yeah, let's check this. Yeah, so the correct answer is the flow condition occurring in the cohesionless soil. So let me explain this. So what is a quicksand condition? So usually uh, in your soil matrix, there are some soil particles along with some voids available, and in those voids you can have the air particle as well as your water particle available there. So at certain condition, your the pressure which is being applied by the water, which we also known as the pore water pressure, becomes in such a way such that the your uh, load coming to that particular point becomes equal. So in that particular case, your particles are not able to resist the load which is coming from the above part, and then your water will come from your
Sir,
soil
your
matrix.
voice is not audible, sir.
Yeah, sorry for that. So let me explain this again. So this is your soil matrix. Your soil matrix basically consists of your soil particles as well as the voids which are having the water as well as the air as well. So there is a certain condition. So let's say when this particular matrix is subjected to, let's say, the vibrational load, and in that particular case, your excess pore water, your pore water pressure, your particles don't have that much contact with each other, and they are not able to resist the load which is coming from the above part due to the loss in the interparticle friction. So in that particular case, your water molecules of water particles will try to exert load on your soil particles, and then in that case your water may also come out to your soil matrix. So in that particular case your flow condition become the quicksand condition, and this type of phenomenon is basically happening in your cohesionless soil. So yeah, that is a quicksand condition in which your water basically come out of the soil matrix, because in that particular case your soil particles are not capable to resist the load which is coming uh, from the superstructure, or like let's say from whatever overburden available above. So that is the part. Any doubt in this, guys? Please feel free to interact. I know there were some glitches initially due to some technical glitches because we are handling this session online, but don't like David from all this thing. Here we are there to learn, so please interact with you among each other as well as with me. And if you guys feel like I'm going wrong in a certain manner and my way of teaching is different, so also you can suggest me some patterns, or you need to go with a higher pace or a little pace. So it's as per your suggestion, we'll try to carry on these sessions. Okay, so if you don't have any queries, let's move to question number 5. Yeah. So again, this is from our fundamental soil mechanics part. A soil having particles of nearly the same size. So what basically it is known is, so whether it's uniformly graded, well graded, gap graded, or none of them. So we do have answers from some of our learners. Yeah, so there are mix of answers. So I request you to please think once again, upon the answers which you have given, and then you guys can revise your answers. Okay, then let's check the answer. Yeah. So the correct answer is A. It's basically uniformly graded. So in a certain soil matrix, again, I'll draw this thing. So let's say when you are having soil particles which are of almost same size, means the diameter of the particles are almost same. In that particular case, we call this matrix as the uniformly graded. Then there's another soil matrix which we are going to talk about. So let's say in this soil matrix, you are having your particles which are of all the sizes. So you are having the larger particles as well, then you are having the fine sand as well, then you are having the boulders available. So you means your matrix is having the all the particles which are available, and in that case it's very dense kind of soil state, because your all the voids are filled by your smaller particles, and then it's become a very dense packing of your soil particles. So in that case we call them it as well graded. And then there's come another condition of the soil matrix, where you are having the soil particles which are of either very large size, or you are having very smaller size, and then you don't have the intermediate size. So you are having the means uneven distribution of the size for the soil particles. Then you are having this much size, then you are having only this size, then this size, then this size. So this is your gap graded condition. This is basically there's a gap in the, or there's a what we say, there is a spacing between the particles which is larger due to the uneven distribution of the soil particles. So that's we call that thing as a gap gradient. So as per our question, it has been asked, we need to select the option which is having the particles of nearly the same size. We call that matrix as the uniformly graded. uh, so yeah, your answer is E. Any query in this? If not, so then let's move to our question number 6. Yeah, so here you need to select the proper statement which links with the sensitivity of the soil. So how basically define the sensitivity of the soil? So let's check the answer. Yeah, so the correct answer is option B. So it's basically ratio of unconfined compressive strength of undisturbed soil. Okay, here the statement is wrong. So it's basically to soil in the remolded state. So like the easy way to remember the sensitivity, like usually we call the sensitivity like for any entity, like if we want to make, if we are applying some external force, or let's say some external phenomena to that particular entity, then to that particular phenomena how your entity is basically reacting. So similarly for the soil part, if I want to say like how sensitivity of your soil is, so in the layman terms or in the easy terms, we want to say like if I am applying a certain force on your soil particles, then how your soil matrix is getting, means to what extent your soil composition is basically getting changed. So in terms of spatial variation, that's what I want to say. So this basically is being calculated as a ratio of the unconfined compressive strength. So that basically you perform the unconfined compressive strength test, and then you compare the unconfined compressive strength of undisturbed soil to that the remolded state, and then you take the ratio of that, and that basically can be taken as the sensitivity of the soil. So yeah, that was the definition in terms of sensitivity of the soil. So you just need to have the idea like how to calculate the unconfined compressive strength. So first you need to take for the soil case when your whole soil is the undisturbed soil, and then again you are going to remold that soil, and then you are going to perform the unconfined compressive strength test. So you take the ratio for both the strength, and then you come up with a certain ratio which we call it as a sensitivity of the soil. So that was the problem. So yeah, any clarification you guys want to have on this sensitivity part, please feel free to discuss, or if you want to add something on that, please feel free to do that. Yeah, if not, so then let's move to our question number 7. Yeah, so the question number 7 is the intensity of the active earth pressure at a certain depth is 7 meter behind the wall backfilled by sand with an angle of shearing resistance of 32 degree and the unit weight of 18.5 kN per meter cube. So you need to evaluate the intensity of the active earth pressure at a particular depth, which is 7 meter behind the wall backfilled by the sand. Then your angle of shearing resistance is given to you, which is 32 degree, and unit weight is given to you, which is 18.5 kN per meter cube. So basically, if you know the active earth pressure formula, you can basically evaluate how to calculate the intensity of the active earth pressure. Yeah, we have one answer. Let's wait for others answer as well, and we'll solve this. Okay, then let's check the answer. Yeah, so the correct answer is option D, 39.8. Let's see how it works. So what has been given to you in question? So you are having a certain wall, and then it is backfilled by sand. So your this particular soil matrix is your sand, and then your phi value is given to you, which is 32 degree, and then your unit weight is given to you, which is gamma is equals to 18.5 kilonewton per meter cube. Then you have been asked to calculate the active earth pressure at a depth of 7 meter behind the wall. So you need to calculate what is the pressure which is acting at a depth of 7 meter from the ground level. So again the active earth pressure is given by K into gamma h. So basically you will calculate what is the effective stress at this depth, and then you will multiply it with the lateral earth pressure coefficient corresponding to the active earth pressure. So we also call it as lateral active earth pressure coefficient, and then which is given by K. So we are having the gamma h. The only demand right now is how to calculate Ka. So in that case, it's given by 1 minus sine phi upon 1 plus sine phi. So the value which is given to you is 1 minus sine 32 degree. Then you are having 1 plus sine 32 degree. So with the help of this, you can get what is the K. So what is the K value, guys, got? I'll do my with my calculator. 1 minus sine 32 divided by sorry, sine 32. So it's basically 0.31307 I'm getting. So for now, for the PA value, your Ka is 0.307, your gamma value which is given to you is 18.5, and then your H value is 7 meter. Then calculate what is the answer for this. So 0.307 into 18.5 into 7. So yeah, the answer which I'm getting is 39.75, which is closer to 39.8 kPa. Okay, yeah, so the correct answer is option D. Guys, any query in this? It was straightforward. Then also if you want to discuss something on this, please let me know. If not so, then let's move to our next question. Yeah, so this is question number 8. So here you need to calculate the deviatoric stress. So sample of saturated cohesion-less soil tested in a drain triaxial compression test showed an angle of internal friction which is corresponding to 30 degree. The deviatoric stress at failure for the sample when it is tested with a confining pressure of 200 kPa. So you need to calculate the deviatoric stress with a confining pressure of 200 kilopascal. So let's see this. So the correct answer is 400 kPa. So how can we solve this? So in a dry and triaxial test, basically you are having a certain specimen uh, where you applied a normal load on the sample above. Then you are also having the lateral pressure which is happening on your soil sample. So that sigma p, and then you are having the, which is also known as the principal stresses. So you are having sigma 1, and here you are having the sigma 3. So your diabatic stress is basically your difference of sigma 1 to sigma 3, and that is the net force which is acting on your soil sample, net stress. So your task is like first to calculate sigma 1, then you need to calculate the sigma 3. So your confining pressure is given to you, like how much it is. So it's a 200 kPa. So your sigma 3 value is 200. Now how to evaluate sigma 1? So your sigma 1 value is given in terms of your normal stress formula, which is given by sigma 3 tan square 45 plus 5 by 2. Then you are having 2c tan 45 plus 5 by 2. Again it has been given that your soil is basically the cohesionless soil. So your c basically becomes 0, and then your this term will get 0. So your sigma 1 is basically sigma 3 tan square 45 plus 5 by 2. Your sigma 3, which is 200, then your tan square 45 plus 5 by 2, right? So that will give you the another stress which is acting on that. So sigma 1 value will be tan 45 plus 50. So this will come out as 600 kPa. And then your diabatic stress, your sigma d is basically given by sigma 1 minus sigma 3. So your sigma 1 is basically how much we have calculated, 600. Your sigma 3 is basically 200. So your sigma d is basically 400 kPa, right? So that's your answer. So question number 8, the correct answer is sigma d equals to 400 kPa. Yeah. So coming to question number 9, if the volume of voids is equal to the volume of solids in a soil mass, then the values of the porosity and void ratio respectively are. So your volume of voids is equal to the volume of solids in a soil mass, then you need to give the values of the porosity, void ratio respectively. So your volume of voids is equal to volume of solids. So this is straightforward. If you know the formula of void ratio and porosity, then it's easy for you to calculate. So let's check the answer. Yeah, so the correct answer is option A. So your porosity is basically given by your volume of fluids to the volume of fluids plus volume of solids, right? And your E is basically given by your volume of fluids to the volume of solids, right? So now your N value, basically volume of fluids is saying is equal. So volume of fluids to volume of fluids plus volume of fluids. So it's basically 1 by 2, which is 0.5. And then your E value, as no, they both are equal, so it will correspond to the 1. So the correct answer is option A. So your porosity basically corresponds to 0.5 and the void ratio basically correspond to 1. So we do have some answers. Yeah. So the correct option is option A. Any clarification you guys want to have upon this? If not so, then let's move to our next question. So yeah, in question number 10, you have been given with, like, let's say if the time required for 50% consolidation of a sample of a clay with single drainage is 24 hours, then the time required to consolidate the same sample of clay with the same degree of consolidation with the double drainage. Yeah, so in one case there is only single drainage there, and then in another case you are having the double drainage. So if you know how the consolidation theory works, so it's easy for you to calculate. And also if you know the relation between the degree of consolidation, then the time constant, and then the time required for the drainage, then you can evaluate, then you can answer this question in an efficient manner. uh, so let's check this. So here the answer is 6 hours. Let's see how it comes. So let's say if you are having a certain soil layer, and usually the layers or the medium which is there, it's above and below, it's both are pervious, so means your water basically can dissipate in this manner also and this in this manner also. Okay, so if it will travel in both the manner, then we are saying it as a double drainage. And if it's only traveling with a single, like either above or below, then we call it as a single drainage. So usually the degree of consolidation, the theory of consolidation gives this relation. So we are having the CVT by H square. So where your H is the drainage path. So this is your time constant, right? So now, yeah, again your degree of consolidation depends on the time constant. So since t is inversely proportional to 1 upon h square, so we are assuming we are we can see that your u is also inversely proportional to 1 upon h square. Okay, so is basically then with the proportion we are having u1 h1 square is equals to u2 h2 square. Now they are saying that okay, degree of consolidation, so they are asking the relation between the time and h square. Sorry, so t cvt h square, so this will come out as for case t1 by h1 square. So your t u is basically same, so the t will also be same. So t2 by h2 square, right? So t1 we need to calculate terms of h2 square by h1 square, and that is basically will multiply by t1. So your t2, so your h2 case, okay, so then the time required to consolidate with the same degree of consolidation with the double drainage. So in your second case, the distance where your water molecule may require to travel becomes half. So that is h2 is 1 by 2 of h1 square, and sorry, the whole h1 square, and then this is your h1 square. Sorry for this. So t2 is basically your h2 square by h1 square to t1. So this is your half h1 square upon h1 square. So your t2 is basically 1 by 4 of your time t1, right? So how much will be your t2? So your t1 is 24 hours, so it's 24 by 4, which will be 6 hours. So the correct answer is option C, 6 hours. So you just need to remember this particular relation between the time constant, which you get it, time constant, distance of drainage path, then you are having the coefficient of consolidation, then the time required for that, then this comes from the 1 degree consolidation theory, and then you can calculate it. Yeah, so I see people have given answer. Yeah, it's 6 hours. Any doubt in this, guys? Okay, if not so, then let's move to our next question, which is question number 11. Again, that's a fundamental question. So what are the factors which are responsible for the bearing failure in the soil? So the correct answer, let's see. Okay, you can take one moment and then we'll see the answer. Let's check the answer. So yeah, correct answer is option D, all of the above. So yeah, bearing failure in the soil occurs due to. So usually failure in the soil occurs when your particles are not capable to offer the enough internal friction strength. So in that case, your soil particles slide over each other, and in that case, basically it leads to the bearing failure. So when it can happen, when the pressure which is coming to the soil particles is very large, or if you are having very limited area on which this force is acting, then again this is a case of lead to a bearing failure, or your soil strength is very less. So either your P is very higher, or your area on which it's acting is very lower, or your material is not having the sufficient capacity. So, so in that particular case, you're bearing failure of the soil occurs. So the correct answer is option D, all of the above. So any doubt in this, guys? Question number 11. It was straightforward. So all of the above, like all the factors can lead to the failure of your soil matrix. Okay, if not so, then let's move to question number 12. So, at what case the erosion basically occurs in soil? Yeah, again, this is straightforward. So, let's explore every option. So, when your loading area is large, definitely this won't lead to your, means this may be condition, but it's not the compulsory condition for the erosion. And inclined routes, again, that doesn't correspond to the erosion. Water flows at high speed over the soil, so in that case we can say, because when there is soil matrix, and let's say you are having a certain flow condition above your soil matrix, so when this particular shear force is larger than the shear strength which is available between the soil particles, then your particles may slide, and this may lead to the removal of this soil mass. So in this particular case, your erosion in soil occurs. and yeah, the correct option is option C. Water flows at high speed over the way. Any doubt in this, guys? Okay, if not so, then let's move to our next question. Yeah. So finally coming to the ground improvement part. So far some of the questions which you have covered, like it's just for like brushing up your fundamentals. Again, the soil mechanics, the foundation engineering in itself is a separate topic which required the whole semester to learn. But yeah, with all the questions which you have covered so far, you can at least get little glimpses what we have learned. So if you can go back and revise that thing again, somewhere these questions will be helpful to have a better revision on those topics. Then let's come to our main content. So from now onwards we'll be tackling the questions related to the ground improvement part. So the first question which is there concerning with the ground improvement technique is like you need to see like how the excavation and replacement method can be used. So I'll be back within 1 minute. Please see this question. So let's see excavation replacement method. So what do you mean by ground improvement? So this is basically enhancing the ground properties such that it is uh, capable to survive under various hazards or various un- hazards means the certain events which can cause the loss of property and lives. so that possibly lead to the hazard. So to basically mitigate that part, we basically enhance the soil property such that it is capable to uh, survive that particular hazard. So there are certain condition in the soil mass where you can't improve the soil by any of the methods, and also your economical calculation also basically shows that it is more feasible to perform. So in that particular case, what you basically do, so let's say if this is your particular ground, and let's say if this section of the soil doesn't have that particular capability to survive the hazard which has been calculated, then in that part what we basically do, we excavate the soil matrix out of the ground, and instead of that loose or the low strength material, we again refill this particular section of the ground with more strong material or with a very high strength material which can bear that particular hazard. Then in that particular case, we call this ground improvement technique as the excavation and the replacement method. Okay. And yeah, so this can be performed for the eliminating the freeze and thaw of the frozen soil, and this can be used to reduce the settlement as well, expansion and shrinkage of the expansive soil. So if you are having the expansive soil, so you can use eliminate the expansion and shrinkage and all of the above. So yeah, so the excavation and the replacement method can be used for all the three things, which is all of the. So any doubt in this? If you didn't get any part, so it's simple. You just remove the soil and refill that hole or that whole ground with enhanced material or the larger strength material or improved soil. So that is one of the like very conventional technique we can say for the ground improvement part. Guys, you want to have a discussion upon on this? Please feel free to ask. If not so, then let's move to our next question, which is question number 14. Yeah. So, what particular case among all these options lead to the liquefaction? So again, we have discussed this thing today also. So in liquefaction, what is the phenomena which is basically happening there? Yeah. So it's simple. The effective state basically becomes zero due to the increase in the excess forward pressure. So let's say if you are having a certain soil matrix which is having the cohesionless soil type, and this is fully saturated, means all the voids are filled with water. Now let's say if I shake this soil matrix or vibrate this soil matrix, so there comes a condition when your all the voids are filled with the water, and somewhere your soil your water particles may come in between the soil particles. So in that particular case, what basically will happen means the shear strength of water, as we know, it's zero, so it won't be able to resist the load which is coming above, because as we know the soil particles resist the load due to the internal friction strength, and in that particular case, since the water has come between the soil particles sorry, and the shear strength of water itself is zero, so the internal friction strength also becomes zero. So in that case, your effective stress basically becomes zero, and this is basically happened due to the increase in the excess pore water pressure, because your water has occupied a larger spatial area in this case. So this will lead to your liquefaction condition. So the correct answer is option A. Your effective stress becomes zero due to the increase in the excess pore water pressure. I guess many of you have given this particular answer. I can see in chat box. Oh, that's great. Otherwise, if anyone want to discuss, have a discussion upon this, please feel free to ask. If not so, then let's move to our next question, question number 15. So, rammed aggregate column is used for. Yeah, Shiva, please.
Yeah, like is this phenomenon happens for a particular type of soil?
Yeah, means usually it's highly observed in the cohesionless soil.
I see.
Yeah, so because the cohesionless soil are having the capability to have a arrangement when they are subject to the vibration, because in the cohesive soil, like, they won't be able to mobilize that much, but when it comes to the cohesionless soil, these particles are capable to have a larger movement as compared to the other soils, and in that case certain section of the soil matrix is being occupied with your water, at water molecules, we can say. So then it basically leads to the decrease in the shear strength within the soil particles because of the introduction of the water molecules. And as we know, the water is having the zero shear strength, so it's nowhere capable to resist the load, so the effective stress becomes zero, and which is has basically happened due to the increase in the excess pore water pressure. So that is about it.
Yeah, another question, is it going to happen under only dynamic loading, or can this happen under static loading?
uh, this happens under the uh, dynamic loading only, because then we are having the larger mobilization of the soil particles. In the static loading, no, as per my knowledge, I haven't seen any case study which basically highlights that.
I see. So, though the effective stress becomes zero when there is a static sustained loading,
uh,
the you mean to say that there won't be liquefaction?
uh, can I get your question again? Sorry.
No, the thing is,
uh,
there's a structure down below the soil got the effective stress zero.
huh.
Yeah. Now there's already the soil is already loaded statically.
Mm.
Can there be liquefaction in this scenario, or in this scenario we only have consolidation?
Okay, so means initially your soil is having a certain superstructure above that, right? You are saying,
Yeah, yeah,
and then there is some static load which is coming from that superstructure,
yes.
and now at a certain depth, you are saying the effective stress has
Have
become
become
zero.
because of the dynamics of the water table. The effective stress have become zero, rising of water table or whatsoever.
Okay.
The effective stress have become zero.
uh,
Now, will there be liquefaction in this scenario?
means it need to be subjective, means due to the increase in the water table, I'm not getting like how it the effective stress is becoming zero. Means though the water table will get increased, but there will be the intactment of the soil particles in between,
Mm.
so that won't lead to the liquefaction condition. Means the rising of the groundwater table alone won't lead to the liquefaction thing. That rising of the groundwater table, coupled with some dynamic loading, then
Oh,
it will lead to the liquefaction process.
yeah, got it. Thank
Yeah,
you.
yeah, that was about it. Okay, thank you. Anything else, guys, you want to have a discussion upon? Please feel free to ask. Okay, if not so, then let's move to our next question. Question number 50. What is the rammed aggregate column is used for? So the name itself can suggest, or if you have gone through the lectures of Professor Pedia, or the slides which has been shared to you, then you can answer this question. Sorry. Yeah, so the correct answer is deep densification. If you guys are having any other answer, please let me. Guys, any concern with the answer? Yeah, sorry. So the correct answer is option B. It's basically the deep replacement. Deep densification can also be like we can have that ground improvement with a rammed aggregate column, but the main motive from the rammed aggregate column is the deep replacement. So you are having a certain matrix of the gravel particles which has been rammed, and then you are having a ground, and then you basically replace a certain column and fill that gravel column in this and rammed your whole column with these gravel particles. So that is basically option B. So in this thing, like you are having a deep foundation type of entity, which is instead of the foundation, you are basically filling that borehole with a certain rammed aggregate uh, geological material, and then you are basically ramming them again and or compacting them again, and then basically it's replacing your the what we can say your unwanted soil mass with higher enhanced geological matter. So that's how you are basically improving your ground. So this phenomena from the ramp aggregate is known as the deep replacement. Then let's move to next question, question number 16. Guys, any doubt by the way in previous question? If not so, then let's move to question number 16. Okay, I think the figure has not been given to you. Okay, so we can skip this question. Yeah, you can address this question now. So ground heave occurs in soil if. So what is the phenomena which is basically leading to the ground heave? Yeah, so the correct answer is option B. So usually swelling pressure is higher than the applied pressure. So let's say if you are having a certain soil mass, when it is subjected to certain external load, so instead of getting swelled up, these particles start moving, and that basically leading to the rising in your soil mass above certain datum level. So if your soil would have been are capable to swell, uh, then there is an increase in the volume, but since swelling pressure is higher, so means your applied pressure is more, so in that case is basically leading to the increase in the whole soil mass. So instead of increasing the volume of each soil particle, your whole soil matrix is basically rising due to the applied pressure. So in that particular case, your ground heave occurs. So let's say if this is the ground, if you are applying some external load, and if your soil is not capable to swell up, so if I just let's do it. So these soil particles, they are not able to swell up like this. So this phenomena is not happening, and instead of this, when you are applying this power force, these are adjusting themselves, and it's leading to the heaving of the ground. So this is the ground heaving. So swelling pressure is higher than the applied pressure. So this is question number 17 answer. Then let's move to question number 18. A project site has a 6-meter thick loose gravel layer near the ground surface that need to be improved for foundation support. The most suitable method for ground improvement. So which ground improvement technique which you suggest for a project site which has a 6 meter thick loose gravel layer near the ground surface that need to be improved for the foundation support? Yeah, so let's check the answer. Yeah, so the among all those options which he has seen, the most suitable option which is can be utilized is the dynamic compaction. So your ground basically is having a 6 meter thick gravel layer. This 6 meter thick gravel layer. So excavation and replacement methods, like it won't be feasible to do that anyway. It's a gravel layer, so it's having a very high, it's very high strength material. So somewhere if you can improve its interparticle packing, then it can be used as a very enhanced material for a enhanced ground. So excavation replacement methods, like it's not a suggested technique. We don't want to go with the traditional compaction method because you want to improve the interparticle packing, so traditional compaction method won't lead to that. Chemical stabilization again you don't want to do because this as we said is very enhanced gravel is enhanced geological material. So we'll go for the dynamic compaction method. So dynamic compaction, basically you will compact this soil along with applying some dynamic or some vibrations to this soil matrix such that it will rearrange themselves, and in that particular case your ground, the overall bearing strength of your soil matrix will get improved, and we call that thing as the dynamic compaction. So yeah, option B is correct. Any query in this? Not so, then let's move to, okay, so I think we can skip this question. Yeah, so you can just address the last question of the day. So match the following and choose correct answer. So you need to select all the proper match between these options. So at left side you are having a certain type of geomaterial, and then what is the potential problem associated with each geomaterial. So you need to match that. So let's check the answer. Yeah, so correct answer is option A. I think some of you have also given the answer in chat box. Yeah, so let's see how it works. So let's go with the expansive soil. So expansive soil, by the name itself suggests like it basically expands. So there's a large like volume change you can expect. So the problem associated with option A is this too. Then with the soft clay, again the clay material are having a very larger problem associated with the permeability. So in this case you are having a problem associated with the drainage, so that's a low permeability. With the loose sand, you are having the higher permeability because this type of sand soil is having very larger void ratio, which is having the higher permeability. Then you are having the solid waste. Then this solid waste is basically, though it has been used as some type of geomaterial, but again, since they don't offer a very enhanced strength, so solid waste is your basically linked with the higher degradation potential. So what is the option which we can go for? So for the A you are having the 2, and then for the B you are having a 3, then C you are having a 4, and then D you are having a 1. So the correct option is option A. So yeah, I think many of you have given this answer. So that was the last question of the day. If you guys want to have a discussion upon on this question, or yeah, is permeability of soak is low compared to hard clay? Uh, that's a nice question. I need to look on this. Mm, I'll get back to this. Like I don't want to make a like approximate statement. So please allow me to have check on this. Do you have any answer on this, or you want to suggest something? It's fine. Yeah. Thank you, Shiv.
No, I don't have. It's all of a sudden
Mm,
flashed into my mind when I saw this question.
mm-hmm. So like
I'm
they are having
very,
certain permeability values. So
yeah,
I am I know the difference between the sand and the clay, but
yeah, yeah.
within the clay, like how does it differ? I'm not sure of that. Sorry. Yeah,
Let's check even.
yeah, yeah. I'll check and I'll let you know. Thank
Yes, sure. Thank you.
you. Yeah. Any other doubt, guys? Like apart from question number 20, you want to discuss? Okay, if not so, then let's call it a day. We'll meet again on next Tuesday, and those people those like just information. We are also going to upload the recording of these videos on the YouTube channels, on our YouTube channels, and the link of that corresponding channel will be shared to you by NPTL team. So you can also refer this video for the future references, and those who are not able to attend this session and those who are watching these videos at a later stage, you guys can post your queries in the comment section of the YouTube videos. uh, we will try our best to address those queries there itself. Thank you so much. So if you don't have any other question, we'll meet on next Tuesday. So this will be having the next 11 weeks dedicated to this type of discussion only. So on every Tuesday at 6 p.m. we are going to meet. So thank you so much. Thank you so much, guys. Thank you.